So we're looking at in-class structure 2 today. And so all I've done so far is just open up the INS file, which is an instruction file. And when you open it up, it gives you a little bit of information. It gives you the proposed unit cell. It gives you the space group and the D-min. So how good of a data collection did you collect down to? So we collected to 0.55 angstroms. I over sigma is not too great. It's 8.5. Our int is kind of high, but our completeness is 100. So this is not a too bad of a structure. Now, if you want to know what the proposed structure is, you can go to the, let me bring it up. You can go to the file, and there's also a JPEG that shows you what the proposed structure is. And let me bring that up so we can see it. So this is what the proposed structure is. So it's this type of organic molecule. So you see we have some oxygens, we have some nitrogen and carbon. So this is what we're looking for when we're solving the structure. So you may want to have that handy so you can refer back to it as we're doing the experiment or data solution. I'm just writing it down on a sheet of paper so I don't have to keep on going. All right. So now let's go back to the OLEX. So the first thing we want to do is we want to do a solve. So if you click on the arrow next to the solve label, it'll bring up the type of program, the HKL file. So you want to make sure that's consistent. The proposed composition. Here is one chance you have at changing the Z value if you want. So here it assumes that our Z prime is one molecule, in this case, in the asymmetric unit. So since there's 4 symmetry operators, we should have a total of 4 molecules in the unit cell. And if you want to see what OLEX suggests on the space group, I mean, from the file, it suggests P212121. But if you click suggest space group, it still suggests as well P212121. So there's a high probability that this is the space group for this crystal structure. Now, as far as the structure solution programs, just to kind of recap, the most common and robust one is ShellXT. ShellXT is the same as ShellXS. The only difference is ShellXT automatically assigns atom types to the electron density peaks. If you use ShellXS, it only assigns atom types to the very large electron density peaks like metals, for example, or very heavy elements. ShellXT assigns as best it can atom types to the most relevant electron density peaks. So ShellXT is by far the most common one that we use. ShellXD is used for very large structures that have hundreds of atoms, maybe like a macromolecule, something like that. Very seldom do we use ShellXD. And then the default is OLEX2, which is a different type of solution program using OLEX mechanics, a little bit different. So for ShellXT, we use something called intrinsic phasing, but for OLEX2, they use something called charge flipping. It's a different method to determine the initial model of the structure. So if you don't have ShellX, you can still follow along with OLEX2.solve. But I'm going to use ShellXT. And ShellXT is only one method, intrinsic phasing. But just to show you a different one, if we go to ShellXS, Shell XS has 3 different methods. The most common one for Shell XS is direct methods, but sometimes I've used in the past, if you have a very heavy element like say a metal, like a transition metal, you can use Patterson methods, and that can help do a better job at doing a structured solution if direct methods fail. But this is the old school Shell X, and so these were the 2 common methods that you use. Most of the time, direct methods, if you had a heavy elements like a transition metal, you can use Patterson methods. I don't think I've ever used structure expansion method. And you can read about how these methods work. That's not the scope of today's talk. So now we'll go back to Shell XT. When you're ready, you click Solve, and it's going to give you an initial model for the structure. And so again, to zoom out or zoom in, if you hold the right mouse button, if you move the mouse, you can zoom in and out. If you hold the left mouse button, you can rotate your structure. So again, all I've done is click on the Solve button. This is the initial model. Now, keep in mind that when you use Shell XT, we may use the same program, but we may get a slightly different initial model. So if yours doesn't look exactly like, if some of the atom types are different, it's okay. But the kind of the general structure should look the same. So we've done our initial model. Now we need to cross-check it with our proposed model and see if there's anything that is not correctly assigned. And so if we start on my left side, you'll see here that this nitrogen, when we look at our proposed model, should be an oxygen. Now for the time being, I'm not going to relabel it just to show you what happens to that atom, but this would be one that you would right-click, go to Type, and select Oxygen, and change it to an oxygen, because based on our model, it should be an oxygen. But I'm going to keep it as a nitrogen for the time being to show you how you can use refinement results to kind of confirm that this should be an oxygen and not a nitrogen. But other than that, the structure solution did a pretty good job. Most of them are labeled correctly. And so now if you want to label your atoms with the common labeling, what you do is you go up to Mode and you do Naming, and you got to do this each time for each different atom type. So if you go to Mode, Naming, and go number sequentially from 1, you can click on the atom type. So I'm going to label this N1 and N2. And you have to have some kind of method in labeling the atoms. You can't just randomly label atoms. There has to be a method to it. Now when you want to label the oxygens, you go to Mode, Naming again, number sequentially from 1, and you go O1, O2, O3, O4, O5, O6. You just click on left click and it labels the atom. And we do the same for carbon. We go to Mode, Naming, number sequentially from 1, 1, 2, 3, 4. And the reason you do this because the naming format that it has, like the C00F, this will cause you a G error in the check CIF. So this is actually the better way to name the atoms. So you don't have to do this at this time. You can do it at any time if you want, but you know, this is how you would name or label the atom types. You go to Mode, Naming, number sequentially from 1 for each different atom type. And again, in OLEX, there are multiple different ways you can do each thing. So if you find a different way to name an atom, you're more than welcome to. Another way you can do it is old school ShellX commands. If you put name say for example, let's see, I'll name C1 C30. And this is the way you can do it one by one. You can type in the command name, put in the label, or the labeling of the atom, and then put next what you want to label it to, and you hit enter. Now you'll see this is labeled C30. So I can go back and say name C30 C1, and now it's back to a C1. So that's two different ways you can name label atom types. Now since we're kind of okay with the initial model, we want to go to the refine, so click on the arrow next to the refine button. And since we're using ShellX as a solve, we should use, it's common to use ShellXL for the refinement, and does a cycle of least squares. And there are two types here, ShellX and OLX2.refine. If you don't have ShellX, you can use OLX2.refine to refine your structure. But we're using the LS stands for least squares, so it's number of cycles it goes through to converge on the model. And so the cycles tells you the number of cycles it goes through, so the more you use, the more likely it's going to converge in one refinement versus doing a series. Keep on clicking on refinement. Usually I set this like 5 or 6. The number of peaks are the number of additional Q peaks that are shown in the structure. We can leave it at 20 for now, but you can go anywhere from 0 to 99. And this is good, as we'll see in a little bit, when we want to identify hydrogen atoms on non-carbon atoms. It's very good to use electron density map from the peaks to determine those hydrogen atoms. The second thing is for this drop-down menu, you want to put ACTA, and what this does is every time you refine it, it updates the CIF file, your crystal information file. So it writes it as you're doing the structure solution. And then when you're ready, you hit refine. And so when we hit refine, where it says solution here, it's going to show us our current R factors for the refinement of our structure. So you see we got a lot of red and yellow right now. That's okay. Looks like a Christmas tree. So again, you see that the shift is red. It didn't converge, but it's almost there. So if you click refine one more time, it should converge. On the structure should converge to a stable form. That means the atoms aren't moving around a lot. So now you see that we've converged to a minimum. Now just a few things to recap. R1 and R2 tell you how the calculated structure factors, which are determined from your model that you're refining, compared to the observed structure factors, which were collected from the diffraction experiment. And so when you compare these two, the closer the calculated R to the observed, the lower the R value. So the only difference between R1 and weighted R2 is weighted R2 uses a weighting scheme to weight the structure factors, whereas R1 doesn't use a weighting scheme. And so R1 will always be lower than R2. Another thing you may notice is that there's an orange, you may have this orange circle here with the arrows next to the formula. If you click on that, it'll update your chemical formula. And now you see it's gone, if you have that. So we've done the initial solve of the initial model. We've refined it because we had, atom types look okay. The next thing we want to do is we want to change how the atoms are illustrated in the molecule. So right now you'll notice that all the atoms have these spheres located, or shapes. And so this means that they're isotropic behavior. That means that the electron density around the atom is spherical shape. So it's all uniform. But as we know from experiments that the electron density around atoms are not per se spherical, they're different, slightly different, maybe ellipsoid shapes. So what we do at this point is we go up to the model and we go ANIS all. And so what this does is it converts the atom types from isotropic thermal parameters to anisotropic. And you're going to see some of these may elongate, looking like a little bit like a football, American football. Now, if you see that they look like a cigar, as we'll see later on, that's a little bit different. That means it's disordered, and you'd have to model that. So when you click on ANIS all, it's going to refine all of them. But let's say, for example, you only wanted to refine a few of them. You could just select the atoms you want, go to model, ANIS selected, and it would only model those that you selected. But then once you click this, you have to click refine to do it. The ANIS all does the refinement automatically. So let me unclick these. We'll go model, ANIS all. So now you see these little cross hatches on the atoms indicating that they're thermal ellipsoids. And you should see a good decrease in the R factor. So now you'll notice that our R factor went from 12 to R1 to 10%. The weighted R2 went from 35 to 29%. As you get to lower R values, this goes from red to orange to light green to green. So a good the best structure is when all of these color boxes are all green. But that's not going to happen right now. And so you'll notice that these atoms now have some shape to them. They're not all spheres. They're kind of elongated shapes, looking like ellipsoids. This does a better job at identifying the thermal behavior around the atoms. So next what I want to do is we want to assign the hydrogen atoms. And so what we're going to do is you'll notice here that you'll see a few peaks. So right here, you notice a peak off this carbon atom. You'll notice a peak off this carbon atom. There's one off this carbon atom here. There's one here. There's two here. These represent hydrogen atoms. Again, there's two here. Now, on this one, you don't see them all because what's happened is we only did 18 peaks. So this is probably number 19 and 20, for example. And so to label hydrogen atoms, there are a couple of different ways you can go about doing this. If you have your toolbox menu open, you can just click Add H, and this will add it and automatically refine the structure at the same time. Likewise, if you wanted to do anisotropic, you can just click on this button here, and it will automatically do anisotropic for the atom types. Another way to add hydrogens, if you click on the tools, you go to hydrogen atoms. Here you can click this add hydrogens, and then you'd have to refine it. Or if there's a particular atom that you want to add hydrogens to, if it's a carbon, if it's sp2, sp3, you can click on one of these buttons. So there's like 3 different ways to assign hydrogen atoms. So the way I usually do it is I just click on this button, but you're more than welcome if you go to the work menu, just click on Add H here and it does it automatically for you. It's just the way that I was taught. I do it based on this. I just click here, Add Hydrogens. And so you'll notice that a lot of the hydrogens line up to electron density peaks. So this tells us that they did a good job of assigning hydrogen atoms. Now, since this one here is a hydroxyl, I'm going to delete this hydrogen here because it's on a hydroxyl. And I'm going to delete this hydrogen here because it's a nitrogen. So typically, with non-carbon atoms, when they have hydrogens, you should determine those by electron density plot. So that's why I've deleted those hydrogens. Again, to remove the Q peaks, if you roll your mouse button up, they appear. If you roll your mouse button down, they disappear. So up, they come back. Down, they disappear. Also, you can use the commands. If you type kill, $Q, it will remove all the Q peaks like that. So there's like 2 ways you can remove extra electron density peaks. So now we've assigned the hydrogens. Since I did it this way, I'm going to click refine. If you just click the add H, it's already done it for you. So and so here our R factors decreased again. We need to change our formula. So we click on the orange button, it updates the chemical formula. Now we need to assign the hydrogen atoms for our non-carbon atoms. So if you look here on this oxygen here, there's a Q peak. That's about, if you go to right click on the Q peak and bang, it tells you that this Q is about 0.93 angstroms from an oxygen. So that tells you that this is possibly a hydrogen atom. So for oxygens, you're looking anywhere from about 0.8 for hydroxyls up to about 1.1. That's an indication that may be a hydrogen at that location. So what you do is you right click, you go to type, you select it as hydrogen. Now on the nitrogen, you'll notice that there is no Q peak off the nitrogen. But maybe it's because we only have 2 peaks showing up. So what we're going to do is we're going to refine this again, and we're going to put 30 Q peaks to see if any peak identifies itself off the nitrogen that we can assign a hydrogen. So we hit refine. And you see by labeling that hydrogen, we've lowered our R value. Now the shift is a little bit high, so we're going to refine again. And we'll refine one more time to converge the current structure. There we go. Now it's green, it's okay. So one thing you need to do when you assign hydrogen atoms based on electron density maps, you need to right click, go to UISO, and again for methyl hydrogens and hydroxyl hydrogens, you're going to set UISO to 1.5x because you don't want to refine the thermal parameters for hydrogen atoms. If it's a hydrogen attached to a nitrogen or an sp2 sp hybridized carbon, you would set it to 1.2x. So now we're going to set this to 1.5x. And again, if we right click on the hydrogen, we do bang, you can see that once we assigned it hydrogen, the bond distance shrunk to about 0.85 angstroms. And the reason you want to assign hydrogens on oxygens and nitrogens by electron density map is because you get a better representation of the hydrogen bond distances when you report them in your structure, because now the hydrogen is experimentally determined, not calculated from the position of the non-hydrogen atom. So now this oxygen is taken care of. Over here on this nitrogen that we labeled, well, I purposely mislabeled it nitrogen, you'll notice that there is no hydrogen off of this nitrogen. So this is a key indication that this probably is not a nitrogen atom. Secondly, you'll see that this atom is attached to an sp3 carbon and an sp2 carbon. So this can't be a carbon either, because then you would have to have, for it to have no hydrogens, you would have to have 2 double bonds, and that can't work because, again, you have a methyl group here and you have a C double bond O here, so there's no way you could put 2 double bonds between this. And if you right click on the atom and go to bang, you see that the bond distances is about 1.33, 1.43. These are going to be a little bit long for a carbon double bond. Carbon double bond, you're looking around, 1.3 angstroms, 1.2 to 1.3. So obviously it can't be a nitrogen, it can't be a carbon, then it must be an oxygen. So now if we go and label this an oxygen, it makes sense because oxygen, there's 2 single bonds off the oxygen, and then that makes sense based on the connectivity, and there's no hydrogens off the oxygens because this is a ether oxygen here. So now if we click refine, if we did it correctly, we should see a little bit of decrease in the R value. And also the thermal parameter should shrink, it should be a little bit smaller. So we had a little bit of slightly decrease in the thermal parameters, but even based on our own chemical intuition, we know that this should be an oxygen. It can't be a carbon or nitrogen based on connectivity restraints. Now you may say, well, how do I know this is a methyl carbon here? So what I can do is, to prove it to you, and I hope this works, is if we delete these 3 hydrogens and then we re-refine it, you'll notice here, let me wait for it to stop. You'll notice here that you see 3 Q peaks off of that carbon. These 3 Q peaks represent the 3 hydrogens. So this confirms that this is a methyl carbon. And if this is a methyl carbon, this has to be a single bond here. So now if we go to tools, add hydrogens. Now it added it like this, but you'll see when we refine it, they'll actually move. See, now they've moved to where the electron density peaks are, and those peaks are gone. So this is a methyl carbon. So this confirms to us that this has to be an oxygen atom. So now I'm going to decrease the peaks, hit refine, just to get rid of all the excess. Okay. So as far as the structure refinement involving the actual model, we come to probably the end of it. The next part is more of the technical things, like how much high angle data to omit, what reflections are bad, adjust the weighting parameters. So that's what's coming up next. But just to explain a few things, again, oh, that's an accident. Again, now since this is P212121, this is a non-centrosymmetric space group. Since it's non-centrosymmetric space group, it's going to give us a flak parameter. And those who joined us on Friday, someone had asked about the flak parameter, and I gave a detailed explanation. But the flak parameter helps you in identifying absolute structure. Just to give you a very short summary of flak parameter, when the flak parameter is close to 0, it means you have the absolute structure. If the flak parameter is close to 1, that means you have an inverted structure. So you would have to invert the structure to get the correct absolute structure when the flak parameter is 1. Now when the flak parameter is 0.5, that tells you you have a racemic mixture. And if you suspect you have a racemic mixture, you may want to investigate a centrosymmetric space group to solve your structure in, because central symmetric space groups have racemic mixtures. So that's the value, and that tells you what the value, each value kind of means. Now, with molybdenum radiation, which is what we collected this data at, for molybdenum radiation to determine absolute configuration from the method called anomalous dispersion, which is what we use, you have to have an atom heavier than phosphorus when using molybdenum radiation to use anomalous dispersion to assign absolute structure with molybdenum radiation. So as you see here in this structure, there are no atoms heavier than phosphorus. So what this means that this Flack parameter is totally irrelevant. It's bogus. Because if you look at the error is just as large as the value. It's 0.1 parentheses 10. That means it's 0.1 plus or minus 0.1, which is obviously ambiguous. So again, since there's no heavy atoms and we collected this molybdenum radiation, we can't assign the absolute structure for this, or we can't confirm it based on the Flack parameter. So what I would tell students in the old days is you have to go put maybe a halogen on it, a heavy halogen, so that we could determine absolute structure. That's why it says in red, absolute structure cannot be determined reliably, because A, it's molybdenum radiation, B, there's no atoms heavier than phosphorus. Now the way you remedy this is that nowadays with the newer diffractometer, it has copper radiation, and with copper radiation, because it's a different wavelength, more powerful radiation, you can have light atoms and still determine the absolute structure based on anomalous dispersion. So nowadays, if I took this crystal, mounted it on the new diffractometer, collected the data, I could determine its absolute structure reliably. So don't worry about the Flack parameter here. It's ambiguous, and if worst case, we just delete it from the CIF file, it's not going to cause a problem. So I've updated my formula. Now, one thing I want to click on is next to the R1, if you click on the percent, it gives you a plot of the observed versus calculated. And what you should see here is you should see a linear trend in the data. So as we go to higher 2 theta, you'll notice that some of these data don't fall in a linear fashion. So what we can do is we can omit certain high angle data to help us get a better fit of the calculated with the observed structure factor. So F observed means the observed structure factors. F calculated means the calculated structure factors. And so as you go to higher 2 theta, you see that the matching of the structure factors is a little bit off. At lower 2 theta, it's a very good job, but at higher 2 theta, it kind of deviates somewhat. There's a little bit of the data falls off linearity. So what we can do is we can do 2 things. First, we can go to info, and if you click on bad reflections, you'll see here that it tells you that the 002 reflection has an error above 10.37. So since it's above 10, you can omit this one if you wanted to. Now what I do is I go to edit, edit instructions, and here we're going to type in a command that's going to omit all the high angle data above a certain 2 theta value. So you type in omit -3 space, and here you can omit above a certain 2 theta value. So for molybdenum radiation, the minimum maximum 2 theta you need is 50. So as long as you omit above 50 degrees 2 theta, you're not going to get any issues with referees and why did you omit so much data. But in common practice, it's good to omit above 55 degrees. Now, if you see that this is not getting your R factor that well, you can lower it to 50, but 50 is the bare minimum that you can lower it to. Because if you go below 50, it's going to give you a check SIF B or A error. And that's not good because they're going to be asking you, why are you omitting this much data? So the common value is 55 for molybdenum radiation. But if you want to go down to 50, you could put 50, but you have to put like 0.1. Because if you do 50 equal, it'll be like 49.99 something. So you have to put like 50.1. That'll minimize it, or that will cut off the 2 theta above 50 degrees. But for common practice, we'll put it at 55 first to see how well the R factor drops. And we should see this 002 reflection over here. It should disappear because now we're cutting off that high angle data. So we click OK. And we click refine. And again, there's like 2 or 3 different ways to omit high angle data. That's just one command that I use as well. So you notice here when we omit it above 55 degrees 2 theta, now our R factor 1 went to 7%, weighted R factor 2 went to 19.2%. So we saw almost a 6% drop in the weighted R2 because we got rid of all that unreliable high angle data. Now if we go to info, you'll notice here that since we omitted the high angle data, now this 002 reflection is not as bad as what it was. But here again, these are just tricks of the trade. Since this error is 9.13 and the next one to it is 6.64 and then 4.72, since there's big jumps in the error, it's okay to delete these 2 reflections because you see it's 9.13, 6.64 is a big jump, and then it's 6.64 to 4.72, and then the 4.27. So here it starts to normalize out, but these 2 are very big, differences. So we can omit those individually. So you just click omit, and now you go to work, refine, and by omitting those 2 extra reflections, we drop the weighted R a little bit more. Now if we click on the percent, so omitted is the data that we cut out. Those are the ones in gray. The orange is what we still have left. Now the last thing to do is to adjust the weighting parameters. And so this helps kind of equalize the reflections because the high angle reflections may not be as strong as the low angle reflections. So the first weighting parameter, it adjusts as you lower it, the R value, the R1 will, or excuse me, the R2 will decrease. But as you decrease the first weighting parameter and the R2 decreases, the goof, which is the goodness of fit, is going to increase. So once you've adjusted the first weighting parameter to a certain value, then you want to adjust the second weighting parameter to get your goof between 1 and 1.1. So goof stands for goodness of fit. So we want that value to be between 1 and 1.1. So we want to adjust the second weighting parameter so that our goof is around 1 to 1.1. Now there's all a balance here, so you can't just put any value for the second weighting parameter. If it goes above a value of 5, then it's going to cause some errors. So we want to try to keep it below 5. And if it's above 5, that means there's something systematically wrong with the structure. You should take a look at it. And so you can do it here, but what I like to do is if you go to edit instructions, you come down here and you see where it says weight. This is the first weighting parameter, and then you put a space and you put the second. So I'm going to do, for example, 0.07 for the first weighting parameter, and we'll put 1 for the second, and we're going to come back and change this as need be. So we hit OK, we hit refine. You'll see that the second weighting parameter dropped by about 2 points, 2.5 points. So we're at 1605. Our goof is 0.929. That's okay. It's in green, not a problem. So now I'm going to go back, lower the first weighting parameter a little bit more. You can go down to 0.01. I'm going to go to 0.05. Hit refine again. So since I lowered the first one, the R is going to drop, but the goof is going to rise slightly. Yep. So now we're at 15.39%. Our goof is still 0.998. So if I wanted to, I can come back, adjust the first weighting parameter. Maybe I'll put 0.03. Again, the goof is still good. It's still green. Green is good. And so this is probably the most I can adjust the first and second weighting parameters to get a low R value and keep the goof between 1.09. If you weren't happy with this weighted R2, I mean, it's below 15%. It's not bad. You know, usually R2, weighted R2 below 15% is good. But you could go back and omit more of the high angle data to see if that helps the R factor. But we can check. And if we went back and checked the bad reflections, you see now we have 2 of them pop up that are bad. And so we can just click omit, because these are very bad reflections because we adjusted the weighting parameters. These came up as being, had a high error. So we can omit them, and it's going to improve our model. So we hit refine again. And since we omitted them, the goof should drop and the R factor should drop. So just by omitting those 2 reflections, you see now we have an R1 of 6.9, a weighted R2 of 13.9, and our goof is 1.01. So that did a better job at fitting the data just by omitting those 2 reflections. Now we come back and just double check. So now there are no red ones, so we can stop here. So as far as getting the R value any lower, this is probably where we're going to plateau. So next we need to go to the report. So you click on the arrow. And here you have to enter stuff in about the crystal. So this is stuff that the X-ray crystallographer would have given you, or it's in the files, the machine files. So you got to put its color. This was a colorless sample. We'll just put it's a platelet. I mean, right now it's okay. The method is the mounting was glass fiber. So either the mounting is going to be glass fiber for older data collections. If it's a new data collection, it'll be called a nylon loop. So that's what goes there. We click on the diffraction. Again, most of this stuff is updated automatically when you do a newer data collection. But for example, the diffraction temperature was 98 Kelvin. 98 Kelvin. These are all things you have to add or it's going to cause a problem. Absorption correction, let's see if it added that yet. No, so the absorption correction type is going to be multi-scan. And you see here the Tmin and Tmax, you get that from the crystalclear.cif file. And so that was 0.762 and 1. Now, as far as absolute structure determination, you want to put this as not applicable because we can't get any kind of structure, absolute structure information from it. Secondly, make sure that this thing that says merge CIF, the box is checked, so that way it updates this information into the CIF file. HKL/regs, sometimes if you put exclude, it'll actually do a better job at using the check CIF in-house than if you were to put leave as is. I usually put this as exclude. Now, if there's any information in the CIF file that you want to edit, you can click Edit CIF Information, and here you can add, anything you want to add to the CIF file. So that way, every time, if it's here, every time you refine, it updates it automatically. So now we'll hit Refine to update all this information. And we're ready to run the check CIF. So you can try to run it through here by clicking on this button, and we'll see if it works today. Last time it didn't work. Doesn't work, we'll just go to the website. Sometimes it works on some, sometimes it doesn't work. It's kind of irate, I guess. So let me stop sharing this and I'll bring up the website. Let me see. You just Google check CIF. And so I Googled check CIF. The first hit is the website, IUCR check CIF. You click on that. And so now you want to browse for the CIF file, so you go to your folder. You want to select the CIF file. So this one's shellx3.cif. Now, if you want to download the file and keep it for your structure, you would click PDF, and this would make a PDF of your report. For us, I'm just going to keep it HTML. Then you go send CIF for checking. Here you're going to upload the FCF file, so you click Browse. You find the dot in the same structure folder. You find the one .fcf. Click on that. Click Open, and now you're going to click Upload. And this is going to tell us if there's any first syntax errors. So maybe you copied a CIF code into the file and you made a mistake. And then it's going to check the structure. So here we have a few A errors that we'll address in just a second. This C error here, let me get my pen up. This C error where it says experimental absorption correction type was given without a literature citation, we can adjust that. This C error here, flag parameter is too small. We can just, I'll show you how to delete that from the CIF file. We can get rid of that, and that'll get rid of that error. These A errors, I'll show you how to fix in just a moment, and we can get rid of those. Alrighty, I think that's all of those. Now let's just scroll up. So what you want to check here is that the sum formulas for the calculated and reported are the same. Similar molar masses, similar densities. The Z values are the same unless you can explain why yours is different from what is calculated. The mu is the absorption coefficient, and this is dependent on the chemical formula and the Z. So if your Z value and chemical formula are off, these mu's won't be the same, and this will cause an error. The F naught or F000 is the, and you'll have to do this for your X-ray project. This is the number of electrons in the unit cell. So after doing all the different symmetry-related molecules, can you calculate F000? And it has our R reflections and weighted R2. So what we need to do here is we need to correct these issues here. And I'm going to show you how to do this here. So what we want to do is we want to open up the crystalclear.cif file in that folder. And at the same time, I want you to go to your OLEX program and click on Edit CIF Info. And it may say update some, so you just click the one for shellx3.cif and update those. So then, let's see. So open in the crystalclear.cif. In that folder, let me share what I see. So I'm going to scroll down, and we were missing, what was it? Let me stop share for a second. We were missing the fraction measurement device type. Cell measurement reflections. And theta min, theta max. Okay. Okay, so we're missing the fraction device method. So you scroll down. So it says here diffraction measurement, the device type. So what you do is you copy this, hit Control C. Now go to your OLEX, and then here at the very bottom, just make a new line and hit Control V. So it says diffraction measurement device type, and it tells you the diffraction device. Now we need the cell measured reflections, cell theta min, cell theta max. So now we go back to our crystalclear.cif file. We scroll up, and that is right here. So you see where it says cell measurement reflections used, cell measurement theta min, cell measurement theta max. We're going to highlight those three lines. Control C. And now we're going to go back to our OLEX. And you go to the very bottom of that and make a new line, and you hit Control V. So now all those three pieces of information, or four pieces, are now in the CIF. And the last thing is the citation for the absorption details. So let me go back one more time to crystalclear.cif. And so for this one, it doesn't have any special details for the absorption. Let me just check. So what we can do to get by this is here where it says experimental special details. Let's just copy that with the question mark. Go back to the OLEX and go to the very bottom and input that. Now hit OK. And when we refine the structure, it should update all that information into the CIF file. So now if you click on the Merge CIF button, this will show you the actual CIF file. And let me bring that up. And you can check to see if that information was added. So now if we maximize, so you see here, cell measurement reflections used, cell measurement theta max, theta min has been updated. Whereas the fraction measurement device type was updated. So now this CIF file has been updated with those things. So now let me go to the check CIF again. And let's redo this check CIF. Again, you open up the .cif file. And then open up the .fcf file. Click Upload Structure Factor. I probably put the Tmin and Tmax backwards. Let me double check that. It said my Tmin was greater than Tmax, so let me just, yeah, I put them in the wrong slot. Let me fix that. My bad right there. 1.00, 7.762. That will. It's still giving us an error for the citation for the absorption correction. Let me see if I can find the citation so that you can see it as well. And then that'll conclude. Yeah, and I'll post this citation for the absorption correction when you use multi-scan in the on Blackboard, because I found it here. Let me see. I think I did. Let me see. Chrysalis Pro. 1 second. Well, anyways, I have to go and look and find that, and I can post it. But it's the C area anyway, so it's not going to cause a problem. So now let me go back, retest the SIF entry. Now we shouldn't have any A or B errors. Yep. If we wanted to, we could go and delete the flag parameter, and it would get rid of this C error. But I mean, this is good enough. You got rid of all the A and B errors. It shows you what the asymmetric unit looks like down here. And so if you were happy with this check SIF file, you could go back and redo it where it downloads a PDF, and you can save the PDF to your folder. And then just to give you some report options that you can do, you go back to ShellX, and you just click on Create Report. It'll actually create a report where it puts all this like bond distances in the table. So if we click Create Report, let me share it with you. It generates this report here. So it gives you all the crystallographic information. It gives you the fractional atomic coordinates, gives you the anisotropic displacement parameters, bond lengths. So here it's where you can determine if there's any deviation in a bond length compared to normal. Say you're looking at a metal nitrogen bond, you want to see if there's any change compared to other ones. This is where you would look. Bond angles, torsional angles, and then this is about hydrogen atoms. Here you can put in stuff and it'll actually write an experimental paragraph for you. Crystal structure determination, information, etc. So all of this is just by clicking on the generate report. And then if you want to look at hydrogen bond distances, what you can do is if you go to Tools, where it says hydrogen atoms, we can expand where it says hydrogen bonds H tab. If we expand this, you see now it's got this interaction with another oxygen. So that tells you there's a hydrogen bond here. So we click on that, it generates the other molecule related by synergy. And you keep on going, you see that we generate a chain of hydrogen bonded molecules. And so this is an infinite one-dimensional chain involving hydrogen bonding. And so you could draw this, create a drawing and show this as a figure in your literature article. So on that note, that concludes looking at the second in-class structure for today. We'll conclude and then we'll take any questions.